see any harm and you guys can start asking questions. I can- What kind of problem? You want to replace both, right? Okay, so. Uh. uh, okay, how about this one? You know, actually, most decks of cards have two jokers, right? Uh. Oh, by the way. One might, think that questions like this might be a possibility in the exam. Certainly they are. You can use a calculator. I don't care. So for example, if you write, the answer is 13, choose 2 times blah, 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 blah. That's good enough for me. I don't need the number. Right, but, if you're nervous about it, you can go ahead and use a calculator. I don't care. Okay. How are we gonna figure this one out? Like, so first thing is what does a 3 of a kind hand look like? All the same things, right? Now, what should we do first? Okay, well, we've got to choose X, Y, and Z, don't we? Let's choose X. How many ways are there to choose X? There's, it should be 13, and you're choosing one, choose my X, right? So that's exactly right. That's exactly right. And that's why we want these different, because if this was an X, it's no longer 3 of a kind, and if these are both Ys, it's no longer 3 of a kind. Okay, so the first thing we've done is we've selected which one is going to triple up. Now we got to count how many there are. How many how many XXXs are there? Right, but there's something else afoot. That's right. So how many X's are there? 5. Well, actually, that's, that actually, there's really 6, right? Because what am I choosing this XXX from? Well, here are the cards that are in play. And more. I was right. There's actually 6. Right? Any 3 of these will make my XXX, right? Everybody agree with that? It could be 3 natural X's, it could be 2 X's and a joker, whatever. So there's actually 6 cards in any of these. So what are my choices on XXX here? How many ways are there to make that?
Six, choose three.
What do we have left to do? Okay, let's choose our kickers. How many ways are there just to choose the ranks Y and Z? Right, so we can't choose the X anymore, so we've got 12 ranks left. And from that, we're choosing two. Right? And what's the final step we need to do here? We need to choose the rank, right, is Y, a diamond, a spade, a club, or a heart, right? Four choices for Y. So it looks to me like the number that I'm gonna get is 13 choose one times 6 choose three, which is yes.
Can you re-explain the double counting thing? Like why you did 12, choose one instead of, 12, choose two instead of 12, choose one, 11, choose one?
Yes. Let me write this down and then. Well, the question is, hey, Jim, why didn't you do this, right? Why didn't you say, hey, there's 12 ways to do this and then 11 ways that I can pick this? What's the problem with that? Well, let me ask you this. Let's suppose I've got 3 10s here. 3 10s, queen, king. Is there any difference in that hand between 3 10s, king, queen? Those hands are the same, right? If you go 12 and then 11, that counts choosing king, queen, and it also counts choosing queen, king. Right? If you notice, if you pick 12 and then you pick 11, this is 12 times 11. But if you look at 12, choose 2, this is 12 times 11 times and that's exactly what it's doing here, is it's throwing out the double count. Right? Yes.
Then why don't you do 13, choose three at the very beginning?
Well, you can if you want, right? But these things are not symmetric. Right? So actually, let's, by the way. Well, we'll do this some other ways. The first thing we can do is okay, I've got 13 choices for my ads, right? This leads at this point, this leads to YZ, right? Okay. Now, let's think about it this way. One thing that we can do is now choose Y. So I'm going to box this off. Okay, let's think. How many ways are there just to choose Y? Let's forget Z. We've got XXX. And we've taken care of this. How many Ys are there? Well, I just mean, think of it this way. When I pick my Y, my only restriction is, at this point, is that I can't pick another X, right? So. Let's see, I had 54 cards because I got a standard deck of jokers. I throw out all 6 of the things that can involve X. And that leaves me with what, 48? There are 48 cards I could have picked. Now that I've chosen Y, how many cards can I pick from Z? How many are left? Yeah, but what if I pick Y again? Right? What if I pick the same rank? Should be 44. Everybody agree with that? So would you multiply this times this times this times this? No, what's the matter with it? You're double counting, aren't you? Right? Because if I get queen, king, this counts 48 times 44, right? But it also counts, the king could have been one of my first, and then queen. This double counts things. So if I wanted to do this, it would be 1/2. Which is why I prefer to use choose. And notice this trailing number is exactly what you get here. Because, right. This is 16 and that's, this is like 66 times 16. And this is, well, this is 16 here. That gives me 3 out, right? This is also 66 times 16. Any questions? Yes.
The Jokers, like, could we do like, could we do like, for choose X and Y, like the suits of X and Y, can we do like 5 choose 1, 5 choose 1 instead? And then do 4 choose 1? Like, how do we know that the Jokers go to like the X?
Oh, that's a good question. My assumption here in these problems always is I make the highest hand possible.
Oh, okay.
Right, so, so if I had, so that brings up another wrinkle that we could explore if we wanted to. If I assume that I go with the highest hand possible, what happens if I get dealt this hand? Three different cards and then a pair of jokers. What, that's gonna be, well, what hand is that gonna be? Well, it's gonna be a 3 of a kind, but I'd have to stick it with the, there's something else it could be also. So, yeah, you would have to go with the highest 3 of a kind, but there's also some other wrinkles here. Right, so actually, from one perspective, we may not have done this problem right, for the following reason. There's a couple other, what else could happen here? If I get a 3 of a kind like this, what do I have to rule out if I assume that I go with the highest hand? Two. Well, here's some problems. So what if I got this hand? 2, 3, 4, joker. What's that name? You can do better though.
This great.
You can do it straight. Right? And there's another wrinkle. What's that? So what we did in this problem, with my two joker problem, is what we naively, what we did is we counted the number of ways to make a three of a kind, right? So this makes your question even more relevant. Because what we did with the computation we did is we count all the ways possible to make three of a kind. But there are some cases when what we call three of a kind shouldn't be three of a kind, right? So for example, if this were the 2, 3, and 4 of hearts and a pair of jokers, we counted that as a three of a kind. And yes, you could play it as a three of a kind, but you wouldn't play a 2, 3, 4 of hearts and a pair of jokers as a three of a kind. It would actually be a straight flush, which is a much higher hand. But on the exam, I'm not gonna make you split hairs like this. This would actually kind of be a nice project. If I wanted to give you a project in this class to go do, is to really separate out what really happens in these cases. But actually, I had a former PhD student, I posed this question to undergraduates for many years. If you've ever played poker with 10-year-old boys, after a while, what happens is half the deck is wild, right? All red cards and kings, you know, and everybody's holding these golden hands. So here's the question that I asked. Poker hands are ranked based on their rarity, and those rarities are computed for hands with no wild cards. That rank is respected even when you add wild cards, with one exception. 5 of a kind is unachievable without a wild card and is considered the highest poker hand if available. So here's the question. If you add enough wild cards to a deck, eventually the most common hand will be a 5 of a kind, right? Think of it this way. If I have 1 trillion playing cards and only 52 of them are regular and the rest are jokers, it's very likely you're going to get 5 jokers and call them 5 of a kind, agree? So the question is what is the minimum number of cards to add to a poker deck before 5 of a kind is the most common hand? And I believe the number is 73. So you can figure these kinds of things out. So at some point, the ranks of the hands will, in a certain sense, reverse themselves. The rarest hand will be having nothing. Anyway, Alex, you want to say something? Ask something.
Yeah, the question, I think this is fall of 2019. Was how many straights are there? in a-
Oh, and I assume no wild cards, right?
No wild.
Okay, let's do this. Let me remind you, and I will assume, because this is probably the way I roll, that you can play aces high or low, right? By the way, if there's ever any ambiguity, ask me. I am not trying to trick you. Well, it's not that way. How many straights are there? Well, okay, and by the way, let me ask you this about the question. Does it say straights that are not straight flushes?
Says how many straights are there? This is a set of 5 cards in a suit, regardless of suit.
Oh, regardless of suit, okay. Well, I'll answer multiple questions. So the question as worded sounds like, I don't care if it is a straight flush, just any straight you want. How are we gonna do this? Okay, that's a great way to, that sounds pretty systematically going. So this is the lowest straight. And what's the highest straight? Start at 10. Here, Jamie's jack. This is the lowest, this is the highest. Given a single straight. Let's see. That's a fixed straight. How many straights are there? Let's look at the low ball. How many straights are there? That form. And of that form, I mean any A's, any two, any three, any four. Right? What's that? What
Okay, sorry.
what I mean is I'm starting with the A's for sure, for sure. I just don't know the suits.
Four to the fifth.
It is 4 to the 5th. Does everybody see where Daniel got that? There's 5 tasks to do. Choose suit, 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 suit. And each task has 4 outcomes, right? So 4 to the 5th. Okay, so if there's 4 to the 5th straights, which is, I guess that's 1,024. There are 4 to the 5th straights that start with A's. How many are there total? Ten times 4. Because every one of these straights, that's a representative straight, every one of them has 4 to the 5th ways to do it. You can start with A's, 2, 3, all the way up to 10. 10 times that. Everybody okay with it? What's that now?
How'd you get 14?
Because what you're doing here, for each one of these, you have to choose a suit. Hearts, diamonds, spades, clubs, and there's 4 suits to choose. So you're doing 5 tasks, and each task has 4 possibilities for it, 4 outcomes, right? What's that now?
I did not know until like.
Because the binomial coefficient selects smaller sets from a parent set. And that's not what we're doing here. We've already selected our set of cards. We're just picking the suits that they come up. So for each one of these, there's 4 tasks. Or there's 5 tasks to choose 4 things, right? Does that clear it up? Now, let me ask you this. This is, I think, the correct answer to the problem that Alex asked on that exam, as I understand it. But if you look it up online, probably, if you go to Wikipedia or some say number of poker hands, it's going to give you a different number for straights than the number we got here. Can somebody tell me why? Right. Some of these straights, I picked any suit. Right. Some of these straights are straight flushes, which would be in a different list. They're ranked higher, right? So how do we count the number of straight flushes? That's right. That's right. So there's your lowest straight flush. How many are there? 4 of them. You can do this with diamonds, hearts, spades, or clubs, and that's it. Right? In starting ranks gives 40 straight flushes. So how many legitimate straights? On the Wikipedia page, what are we probably going to find if we ask really for the number of straights? Right. This remove the straight flushes, and then now you've got all the straights that are not straight flushes. What if I asked you this? This is actually, it's kind of funny. So let me ask you a more fundamental question. No wild cards. Here we're doing the computation. No wild. I'm gonna choose X first because it's the one on the pair. How many ways to choose X? 13 things. Okay. Now I've selected what my pair is in. How many pairs are there? How many pairs are there? Now that I've selected my rank X, how many different pairs are there in that rank? There's 4 X's, and I'm picking 2 out for my pair. Okay with it? The next thing I would do is choose not X. Well, I'm gonna choose. I've got 3 kickers. I'm gonna choose. All right. How many ways are there to pick that? Okay, 12 ranks left over. Pick 3, and this 12 choose 3. It prevents you from going through cases and worrying about double counting and so forth, right? Then. All right. Suit. Four choices. So the number of pairs should be 13 choose 1 times 4 choose 2 times 12 choose 3 times 4 choose 1. And I am curious, so let's see, get something out of this here. There we go. Six. I get like, that sounds right. A little over a million, 1,098,240 pairs. Let me, yes,
Oh, this is about like flushes.
let me ask one question before we get to that. How many hands are there that are nothing? Right? No pair, no flush. no straight, so- What's that? Well, right, but I mean, you legitimately, so. Let me state my question precisely. How many hands are there, when you look at your hand, the best you can do is high card? I mean, the first thing that you would. I mean, here's what has to happen. I'm gonna run out of letters, X, Y, Z, all those five have to be different, right? But now you run into complications. What are the complications? So the first thing you might say is, okay, how many, I choose X, Y, Z, A, B, how many ways are there to do that? 13, choose 5, right? And so that gives you my X, Y. And here's what that does, that tells me that now I've got 5 different cards. But you've still got problems that are avoided by even a pair, right? What if all 5 cards have the same suit? Right? The pair eliminates this possibility. Right? What if all 5 of these cards are in some sequence, so it's a straight? The pair also eliminates this possibility. Counting nothing is actually more difficult. In fact, maybe the easiest way to do it is count everything that's not nothing and subtract it from the total number of hands, as a matter of fact. And in fact, that's usually the standard way to do that. All right. How many hands are there? That's a good kind of question. How many poker hands are there? 52, choose 5. That's right. So one way to do it is that put your 52, your 52, choose 5 over here in the bank and compute the number of pairs, number of 2 pairs, 3 of a kind, straight flush, straight flushes. That's the way you roll. And then put all that together and subtract it from 52, choose 5. So what was your questions? Yeah.
Didn't 12 choose 3 and when we do 4 choose 1.
Right, so there's 2 things going on here. The 12 choose 3. So for example, if my pair is in kings, then my kicker has to come out of, my kicker has to be 3 different things that come out of all the cards that aren't kings. Right.
So it's. So that's why.
These are the ranks that aren't king. And I'm picking 3 of them.
So that's why you don't do 13 choose 2.
Right, because the first thing I did is I isolated this. Because it's not symmetric. XX is doing something different than the other 3. Right? Once I've done this, this chooses my kickers. Now each kicker, here's what I know about the kicker. I don't know everything, right? I just have narrowed the suspect list down. My kickers look like this. I know this is a 7, a 4, and a 2, for example. What I don't know is what's your suit, right? So that's why there's 3 of these. 4 choices for the suit of Y, 4 choices for the suit of Z, 4 choices for the suit of W. Those are the 3 tasks that I need to kind of round it out. So does that make it smoother?
Explain 4 choose 2 or choose XS.
Right. So the first thing I do is I choose X, right? Maybe I've got kings, right? 13 choices, kings what came up. But now, what pair of kings is it? These 2? Actually, let's go through this. It could be 1, 2, 3, 4, 5, 6, which is 4 kings. Pick 2. That's what that does for you.
Like, what would happen if you have a joker and you're looking for straight? Like, if you have one, if there's one, or is it standard to have two jokers? But like, if you add a joker to a deck, like, how does that change, like, how many strings? Like, does that move it down
Oh.
to like,
Oh, okay, so let's do that. Let's, please, have mercy on me. Let's put one joker in the deck and see how many straights we get. Let's see if we can do that. So this is, I may regret answering your question. Let's see what happens. Well. Okay, so I'm gonna start this problem by being naive and I'm gonna count. Um. The first thing I'm gonna do is I'm gonna count all the straights, including the straight flushes. Okay, that's what we'll do first. All right. So first, so I'll make that caveat. So first we'll include straight flushes. Okay, so. Uh, Already done that problem. This is the number with no joker involved. So what I'm gonna do is I'm gonna try to count. Uh. Try to count with the joker, right?
Is it 4?
Oh. You were correct. Thank you. That's very quick. There we go. I inadvertently swapped 5 4. Huh. Now. Let's see if we can see that. So in general, what we can do is. Uh. Yeah, so I see there's gonna be kind of a problem counting this. Um. So my first instinct would be like, okay, for any straight, you can have a joker appearing at any place in the train. What's gonna be the problem with that? So for example, here's what the problem's gonna be. You could have. Doing this, right? And the idea is you sweep that joker through and then you just kind of multiply it by 10. But the problem is this is for ace, 2, 3, 4, 5. But see, well, yeah, I guess what we can do is we'll have to count some, separate ones. Does anybody have any idea on how we can count the straights with the Joker in it? I think I see how we can do this.
I feel like for at least the first piece, there was, are all the pieces sort of like have, like, you have the joke of these.
Well, right, so, no, you can't have the Joker before the ace, so there might be kind of some, actually, he makes a very astute observation. You can't have a Joker before the ace, well, unless the ace is played high, you can't have the Joker lower than the ace, you can't have a Joker higher than the ace, right? So there are these kind of degenerate cases, most straights have cards that are both higher than lower, but there are two straights that have no cards below and no, there's one straight that has no cards below, and another straight that has no cards below. But I think, let's see, yes,
You should not do it by just looking at there being 5 options for the Joker to be in each one of your original 10 straights. And then find the number of enumerate all of them.
well, that's the problem. Because here's what happens. So his idea is, in every one of these straights, the Joker has 5 options, right? But the problem is, if you have well, let's see, maybe you're on something here, so given any straight. Okay. I guess. Let's say X, you can have. Well, let's say, given the straight. X plus 1, X plus 2, X plus 3, X plus 4. I guess you can replace any rank with a Joker, right? Okay, so maybe we're on to something here. So let's see. So when I replace a rank the Joker here. So for example, if I go X plus 1, Joker, X plus 3, X plus 4. How many ways are there to do that? Now remember, the X is fixed. I think it's 4 and 4. These ranks are all predetermined. There's only one Joker, so that Joker has to go there. 4 choices here, 4 choices here, 4 choices here. 4 choices. I agree. And I guess the Joker could replace any one of these ranks. Doesn't matter which one. So. Joker could go in any of these 5 places. Looks like 5 times 4. I agree. And every one of these is different. Yeah, so I guess there's gonna be 10 of them, right? X can range from ace through 10. Start here. Yeah, so I guess that's the best way to, after fiddling around with it, that looks like the best way to do it. So given any X here, whether it's ace through 10, this is one set of straights. If I insist there's a joker, it can occupy one of 5 places, and you've got 4 of the 4 choices on every one, right? So every one of these should be a different hand. So it looks like we get, with jokers, it looks like we get 10 times 5 times 4 to the 4. Right? There's an extra factor of so this is actually 5 squared times 2 to the 9th. And this is 5 times 2 to the 11th. Wow, so that's, see, that's an extra 4 here. Yeah, so there's almost as many this way. So it looks to me like, and this is counting straight flushes, it looks like without jokers and with jokers. So that's gonna be 25 and 20. Yeah. 2 to the 9th times 45. So more than 45,000, something like that. Any questions on that? So, yeah, so it's a little harder to count the straights, right? Than it is to count the pairs and stuff. Okay, other questions? Yes.
I was wondering, this is also what exams. I was wondering if you could go through like, question 2, like, maybe like A through C. And E, actually, I guess all of it,
This is exam 2 from,
28, or fall 28.
oh, for the following sets classified as finite, denumerable, or larger than denumerable. Okay, all right, so here's our goal. I want you all to tell me, are these sets finite, denumerable, or larger than denumerable? Okay,
And
I-
does larger than renewable just mean like, it's like, compared to like the natural, like, it's not 101.
yeah, that's right. It means larger than denumerable means there's no bijection from the natural numbers to this, and it's infinite and there's no bijection. Okay, the set of all atoms in the observable universe. Finite. the set of functions from A to A, where A is the set of atoms in the observable universe.
Right.
Also fine. Humongous, but fine, right? The open interval from 0 to 1/1000. So the interval on the real line starts at 0, ends at 1/1000. Be more specific.
Larger than the number.
Larger than the number. Very good. Well, because do you know the interval from 0 to 1 is not denumerable?
I don't know.
That was the Cantor diagonalization argument. Remember where we tried to make a list, like there's a 1-to-1 and onto function from the natural numbers into the interval from 0 to 1, and I constructed that wonky decimal. It couldn't possibly be in the image. And there's no difference between the interval from 0 to 1 and the 0 to 1/1000. That's what that homework, remember, every interval of length AB, they all have the same size.
And 1/1000 are continuous, does that change?
No,
Okay.
it's still larger than denumerable.
So is that? You didn't have to justify it.
With a problem like this, I don't require that you give me a reason, just an answer is right. But it wouldn't hurt to add something, like, I know this because something like this, right? Because when you screw it up, that makes me more sympathetic, right? Script P, the set of positive prime integers. Denumerable, very good. We know that there's infinitely many primes. I think I proved that earlier in class, way back when. And it's a subset of the positive integers, so it has to be denumerable. P of script P, the power set of the positive prime integers. Larger than denumerable. Okay, you've totally conquered that problem. Wow, what? That's Cantor's theorem.
I know it has to be larger, but I think that's just not larger. Or is that possible?
No, so so Cantor's theorem. A is any cell. And this is the truly sexy thing about this theorem, it doesn't even have to be finite. Then now, the previous problem on that, we know that that set was denumerable. The power set has got to be larger than by Cantor's theorem.
I know that theorem, but I thought there were multiple, like, I don't know, I thought you have a minimum set and then a technically larger set, but is that not true?
That's not true, because what it means to be technically larger is that there is a 1-to-1 map there, but there's no bijection, right? I know there are sets that look bigger, right? I think that what you meant when you said technically bigger is something like comparing the natural numbers to the technically bigger integers, right? Looks like it, right? Because the natural numbers are a subset of the integers, right? But there is also, so that is a map from the natural numbers to the integers that is 1-to-1, but not onto, just inclusion, right? That's the weird thing about infinite sets. But there exists a map from the natural numbers that covers the integers. And so they're actually the same size, right? All denumerables are the same size. It's always a 1-to-1 and onto map. Okay, anything else? All right, well, you guys got the juices flowing for the review session, I hope. Don't forget, 5 o'clock this afternoon, somewhere. It's in one of those round table rooms. It's classic here, but we will persevere.